So from the same section, we jump into this idea of relations. So let's see what's going on here. So relations, the relationship between perpendicular lines suggests that more general but undefined mathematical concept of relation. In general, a relation connects two elements of an associated set of properties, or objects, excuse me. So in this case right here, we see table 1.8 provides several examples of the concept of a relation. So equal to relation says, like in this case here, we have 2 plus 3 is equal to 5. That's a relationship of equality. We have a greater than relationship or relation, and that's where 7 is greater than 5. We have a perpendicular relation, and that's where line L is perpendicular to M, excuse me. We have complementary, congruent, and is a brother. So that's just like a generic example of how you see how relations work. There are three special properties that may exist for a given relation, where A, B, and C are objects associated with relation R. The property is considered one object reflexive, two objects is either order symmetric, or three object is transitive. So if you're just giving like one object, then we can say that's reflexive, like A is equal to A. So A is equal to A, or two objects, we say, let me grab my pen real quick. So there's two objects, we might say something like, oops, get back there. Pause. All right, so like for example, if we had just one object, what might happen is that we would say like A is equal to A, and that would be reflexive. If we had two objects, we might say something like A times B is equal to B times A, and that would be symmetric. Or if we had three objects, we might say A times B times C is equal to A times B times C, and that would be transitive. For properties to exist, it's necessary that the statement be true for all objects selected from the associated set. So as we keep building towards this, like hopefully this will start making like kind of connecting and like letting you see like, oh, this is how I can apply this in this particular situation. So these properties are generalized and specific examples are given below. So this is kind of what I talked about. So like ARA, so 5 is equal to 5, that'd be called the reflexive property. Or the symmetric property would be A is related to B and B is related to A. So like for example, if L is perpendicular to M and M is perpendicular to L, then therefore those perpendicular lines has a symmetric property. We have the transitive property is that like A is related to B, B is related to C, so therefore A is related to C. So slightly different than my examples, but very similar in the idea of how we're going to apply them. So in example 2, does the relation is less than for numbers have a reflexive property, a symmetric property, or a transitive property? So solution. Because 2 is less than 2 is false, there's no reflexive property. If 2 is less than 5, and 5 is less than 2 is also false, then there's no symmetric property. So then the property that would hold for this particular situation with this idea of less than would be is that 2 is less than 5, 5 is less than 9, so therefore 2 is less than 9, and that would be a transitive property, and that would hold in this particular case. So the same results are obtained for choices other than 2, 5, and 9. So relations, the idea is that the idea of congruence of angles or of line segments is closely tied to equality of angle measures or line segment measures by the definition of congruence. So this is a great example of how you'll apply these different relations. So the following list gives some useful properties of the congruence of angles. So for reflexive, angle 1 is congruent to angle 1. So that's the angle is congruent to itself. Symmetric. If angle 1 is congruent to angle 2, then angle 2 would be congruent to angle 1. Sorry about the symbols again. And then lastly would be transitive. So if angle 1 was congruent to angle 2 is congruent to angle 3, then angle 1 would be congruent to angle 3. Now, as we can see from this image, this is not drawn to scale. So it's not like if you're looking at this, you're like, that is not a true statement. That's not, we're just like saying that if this was the scenario we were dealt with, then this is how we could work our way through. So any relation, such as congruence of angles, that has reflexive, symmetric, and transitive properties is known as an equivalence relation. If two lines intersect, then the vertical angles formed are congruent. So in this particular situation, like what we see is that as we look through the proof inside the textbook, we start off by saying that we have this intersection between the two. They intersect at point O. Well, our goal is in this particular situation, we're trying to prove these two angles are vertical. What happens is that we're trying to get this spot where we can say that angle 2 is equal to angle 4. So let's take a look at this picture. So we're trying to get a spot where we can see that angle 2 is equal to angle 4. To get there, what happens is we say, okay, well, they intersect. That's given. All right. Since they intersect, then we can then start saying that we have that angle AOC. So AOC and DOB are straight and they add up to 180 degrees. So we're just like trying to establish some guidelines, some foundations. That way it's like understood. All right. Keep going. Angle AOC and DOB are equal. So AOC and DOB are equal. Well, they're both 180 degrees. So we're just using substitution to establish they're equal to each other. Then we start breaking it down. We start saying that angle 1 and angle 4 are equal to DOB. So angle 1 and angle 4. So we're just establishing that we can build angle DOB with those two angles. We do the same thing with angle 1 and angle 2. So angle 1 and angle 2 add up to AOC. And here I am. All right. And then I get to the spot where I start saying, okay, well, if DOB and AOC, we've already established they're congruent to each other, then let's go ahead and set these new statements by substitution. We can say that they're equal to each other. Then we can use the subtraction property of equality to get rid of the angle 1 and say, okay, well, now we have angle 4 is equal to angle 2. So therefore, angle 4 is congruent to angle 2, or vice versa, angle 2 is equal to congruent to angle 4 by symmetry. And so that's kind of how we work through those proofs, is like getting to the spot where we're like comfortable with like placing these values or these definitions to justify these statements that we're putting in place. And then I'm going to go ahead and finish this video with just like talking about the constructions. I don't have a plan right this minute for like what I'm going to do with constructions for this particular semester. In the past, I've had students do constructions to kind of like just practice this since it's a teacher-based course. So this is a situation where like these following slides are nothing more than just like talking about like how would you construct these perpendicular lines. And so it talks about like using a compass to be able to swing those different like curves, and then talking about how those will tie into our different theorems. And that wraps up 1.6. Let me know if you have any questions. Thanks.